Dharni, you can start now.
Okay, sir. Good evening to one and all present here for the IEEE International Webinar Series SAVANT 2.0. I am Dharni, IEEE Student Chairperson of Women in Engineering Society from the Department of Electronics and Communication Engineering on behalf of St. Joseph's Institute of Technology here to volunteer for today's session. Now I invite Ms. Meera Ganesh, the Student Chairperson of IEEE Robotics and Automation Society to deliver the welcome address.
Thank you, Dharni. Learning gives creativity. Creativity leads to thinking. Thinking leads to knowledge, and knowledge gives us power. A very good evening to one and all present here. It gives us immense pleasure to be a part of the International Webinar Series SAVANT organized by IEEE. On this pleasant evening, we would like to cordially invite Ms. MADELINE Nolan as our honorable speaker. We would like to thank you, ma'am, for accepting our invitation and joining us to share your skills and experience. We welcome you, ma'am. Our respect and gratitude to our chairman, Dr. B. Babu Manoharan, sir, our managing director, ma'am, Mrs. B. Jessipriya, director, sir, Mr. B. Sashi Shekhar, our respected principal, Dr. P. Ravichandran, sir, who have always been a great source of inspiration to all of us. It is our pleasure to welcome our HODs of EC department, Dr. C. Nyana Kausalya ma'am and Dr. G. Rohini ma'am, and all our EC staff members and IEEE staff members who have constantly motivated us. We welcome you all. Last but not the least, I welcome the future innovators gathered here to ignite their passion. It makes us so happy to welcome you all to make this event a grand success. Over to you, Dharni.
Thank you, Meera. I will be sharing a few words about our speaker of the day. Ms. MADELINE Nolan is the president of the Advanced Television System Committee, widely respected for her consensus-building leadership style. She chaired the ATSC technology group that oversees the ATSC 3.0 Next Generation Broadcast Standard before being named ATSC president in May 2019. Previously, she chaired various ATSC 3.0 related specialist groups, ad hoc groups, and implementation teams since 2012. A 15-year industry veteran, Ms. Nolan held key technology management and standard roles at Backchannel Media, Telview Corp, and LG Electronics. She received TV News Check's 2019 Futurist Women in Technology Award and was named one of 2018's Powerful Women in Consumer Technology by Dealer Scope magazine. In 2016, she received the ATSC's highest technical honor, the Bernard J. Lechner Outstanding Contributor Award. She graduated with distinction from the University of Massachusetts. We welcome you, ma'am. So before we start the session, I would like to say a few instructions to be followed by the participants. Kindly post your queries and questions in the chat box. There would be a question and answer session in the end of the webinar. The attendance link will be posted at the end of today's session. Now I invite our speaker of the day to kindly start the session. Ma'am.
Thank you very much for the kind introduction, and thank you to all who are attending. It's my pleasure to be here and my pleasure to talk with everybody here in the IEEE SB webinar. So we'll start the slideshow. A quick overview of the agenda. We will first discuss a little bit about ATSC and digital terrestrial broadcast standards. And we will also talk about the development of ATSC 3.0, the latest television standard, some of the technical advancements in ATSC 3.0, and then we'll also connect them with the heterogeneous network ecosystems that are developing with 5G, LTE, Wi-Fi, Internet protocol, and broadcast systems. And I would also like to discuss some specific use cases for the system for India. And at the end, we can have some summary and Q&A, which I think our kind hosts will be moderating. So just a little bit about standards development organizations. I think maybe this slide is not necessary because this is affiliated with IEEE. However, we can just discuss briefly what is a standards development organization. We create technical documentation that enables industries to move forward quickly by reducing fragmentation, and the standards allow companies to produce products that can be reasonably expected to interoperate with other products. So for terrestrial broadcasting, the broadcast airwaves and the content must interoperate with the receivers, such as TVs, radios, and the like. So here's a good example of a standard in operation. So you have a battery and you have a flashlight. Everybody knows what the battery looks like, how big it is, how much power it is, how wide it is, how long it is. And so any company can build a battery, and any company can build a flashlight because they know exactly what the batteries look like and how big the chamber needs to be in order for those two products to interoperate. So this is a good example of a good standard. Everybody knows what it is and how to use it. This is maybe not such a good example. So you have mixed standards, proprietary solutions for example, cell phone batteries. You can't just go and buy any cell phone battery and put it in any cell phone. So this is an example where standards are maybe not so much involved. So the television standards, as I mentioned, is for terrestrial broadcasting, airwaves and content interoperating with receivers. ATSC, Advanced Television Systems Committee, we were founded in 1983, so roughly 35 years old. Open due process organization, like many SDOs. And the mission statement is to create voluntary standards and recommended practices to advance digital terrestrial broadcasting. We have about 150 members. They are from all over the world, including from India, as well as from Asia and Europe and the US and North Canada, Mexico, etc. So, it's a very exciting time for us. So a little bit about digital terrestrial broadcast standards. There are 4 digital terrestrial broadcast standard organizations in the world today. There's the ATSC, there's the DVB, which is based in Europe, and that standard is primarily deployed in Europe, Africa, India, much of Asia, but not China or South Korea or Japan, Australia, New Zealand, and places like that. And then we have Association of Radio Industries and Businesses, which is based in Japan, and they're primarily deployed in Japan and most of South America. And then we have NRTA, National Radio and Television Administration, which is based in China, and the system is primarily deployed in China. So today I'm going to talk mostly about ATSC and a little bit about DVB because DVB is deployed in India. So there are 2 generations of terrestrial broadcast standards. And here is the list of these organizations and which standards are available today. For ATSC, we have ATSC 1.0 and kind of 2.0. I won't talk much about that. And then we have a next generation standard called ATSC 3.0. And with DVB, there's DVBT and DVBT2. And then Arrive and NRTA both only have first generation standards, but they are working on their second generation standards. So a little bit about DVB-T2 and ATSC 3.0. These are the 2 second generation broadcast standards. So DVB-T2 was the first next gen broadcast standard, and it was completed in roughly 2009. ATSC 3.0 was the second one, completed roughly 2017. ATSC 3 and DVB-T2 have very similar spectral efficiency, good performance, and similar audio video capabilities. There are some differences. ATSC 3.0 uses Internet Protocol, and DVB-T2 uses MPEG-2 for transport. And the ATSC 3.0 system uses web technologies along with WebSocket APIs for interactivity, and DVB-T2 uses the HBB-TV system. So India uses the DVB-T standard, and some cities have migrated to DVB-T2. India may be exploring using ATSC 3.0 for certain use cases. And in order to help work on those projects, ATSC has an MOU with TSDSI, the India Telecom Standards Development Organization, and an MOU with IIT Kanpur for the efforts that they're working on with a Center for Excellence in Broadcast. And ATSC has formed an India implementation team to support the specific requirements for India for 3.0. And we've also formed a planning team on core network technologies for broadcasts. And this work may also be highly relevant to India use cases. So just to stop a minute and talk about India, my understanding is that many people in India watch TV not on a regular television set like some places do, but they watch TV on their phones a lot. And so we'll talk a little bit more about using the television airwaves to reach a direct to mobile kind of service. But we'll talk about that in a minute. So I understand that there are many people on this call who are students, and so to think a little bit about your careers. And it's interesting because many students don't think about opportunities in standards development, but all of these organizations like ATSC, DVB, TSDSI, IEEE, they all have opportunities for people for their work. So what kind of things do people do? Most people working in standards don't work for the standards development organization itself. They work for a company that has a material interest in the work that's happening. So some member stations for ATSC, for example, are Samsung, Fox Television, Dolby, LG Electronics, where I used to work. 3GPP has ones like Qualcomm, Nokia, Samsung. So all of these companies have people that represent them in these standards bodies. So those of you that are interested in standards development could easily work for one of these companies and represent them in these standards developments. Some of the things that happen, people involved in the standards development can participate with the standards process itself, but many of them actually work behind the scenes. So I was representing LG in many of the meetings with ATSC, but there was a whole team of people behind me who were working on the contributions, the patent development, the intellectual property. And there are different kind of skills that different people need. So if you're participating in the standard process, you usually have a great understanding of technology, you have good communication skills, you have an instinct for consensus building. And if you start to display some leadership skills, you're often asked to chair some groups. So anyway, it's a wonderful career, great networking. You get to know everybody. Everybody gets to know you. You're kind of on the vanguard of the next big thing because standards development organizations are usually 5 to 10 years ahead of where the marketplace is going. It's a wonderful niche role, and there are many growth opportunities. So I encourage everybody to think about standards development as a career. So let me get into ATSC 3.0 in more detail. So what were the goals? Why would we develop a next-gen television broadcast standard? We already had ATSC 1.0. It's a digital standard. It works pretty well. So why develop something else? Well, we wanted to add the value to the broadcast platform, new business models, and reaching more viewers on more devices. So the ATSC 1.0 and DVBT standards aren't very good for reaching mobile. To address changing consumer behavior, so providing higher quality video, better audio, more accessibility, and being able to follow the viewers where they are. So one of the most important goals about ATSC 3.0 is that it's not just about television anymore, and I'm going to talk about that as well. But meantime, who was developing this 3.0 standard? There were about 400 individuals, 150 organizations, and lots of participation across the world. It was really the best engineers across the world were working on this. So some key advancements is better capacity. We have our spectrum. It only has so much capacity to send data to devices. And with the new physical layer design, we get more channels, more pixels, more data to go through the same spectrum band. We have better reception, so better for indoor, for vehicles, for mobile. We have hybrid over the air and over the top. It's an all IP-based system, so converged networks is one of the key pieces. We have a better consumer experience with better audio, video, accessibility, interactivity, and advanced emergency messaging. And one of the most important things is new business models. So advanced advertising, pay-per-view subscriptions, service usage reporting, and this last arrow, datacasting, is extremely important, kind of the smallest little arrow on this screen, but perhaps one of the most important ones. So a little bit about the physical layer. This is the ability of the spectrum to carry data. In 1.0, we were able to send about 19.39 megabits per second with a pretty good reception. You can reach the rooftop antennas. With ATSC 3.0, we have much more flexibility in about the same robustness. We can reach mobile and cars and rooftop antennas, and we can send almost 30 megabits per second instead of 19. So it's a much better improvement for the physical layer by itself. This is another example where you see it says A53 there in the middle toward the bottom of the screen. This is where ATSC 1.0 and DVBT roughly operate. The green line is DVBT2, and the red dots forming a line is ATSC 3.0. You can see that DVBT2 and ATSC 3.0 are very close together, almost reaching the theoretical limit of how much data you can move through the system given the signal strength that you want. It's always a trade-off between how strong is the signal and how much data can you send. So you can have a very robust signal at low capacity, or you could have a very high capacity but less robust signal, depending on where you want to operate. In ATSC 1.0, you have one operating point, which is A53. In ATSC 3.0 and DVBT2, you have a continuum that you can operate at any point along this line. And you can operate at more than one point at the same time. So you may decide you want to have a mobile service, which is low capacity but more robust, and a fixed service for rooftop antennas, which is high capacity but less robust. All these things are possible in the system. A single frequency network is also an important improvement for 3.0. It allows the signal to be riding on the same on multiple towers in the same frequency at the same time. And what this does is it allows you to increase your coverage area. The other important piece about this, and this is important for the India use case, is that you can run the ATSC 3.0 system on a traditional television tower, which is a high tower, high power, reaching a large geographic area. But you can also run the system in something more like a cellular network, where you have many more towers. They're shorter, they're lower power, and they're put together in a more densely packed. So you call it low power, low tower, dense network. So ATSC 3.0 can operate in high power, high tower systems similar to today's television airwaves. And it can also operate in low power, low tower, dense network, more like cellular network. So this is an example of one television tower, high power, high tower, sitting in the middle of Washington, D.C. If we add a few low power, low tower in single frequency network to strengthen our signal, we can increase our coverage dramatically with our signal. And we can also connect regions along corridors in order to make a regional service. So another thing that's important, and I won't spend so much time on each of these slides can be available for you after the webinar to look at in more detail. This is a basic signaling hierarchy of the system. And the most important thing about this is the one thing that's sitting there on the left side of this diagram called the bootstrap signal. And the bootstrap serves as a robust universal entry point to the waveform. It's the first thing the receiver finds, and it tells the receiver everything else it needs to know. And the bootstrap is extremely important for a couple of reasons. One is that it's extremely robust and very easy for a receiver to lock onto. And the other is that the bootstrap tells the receiver everything it needs to know, which means that the receiver is not designed in advance with assumptions. The receiver assumes nothing. And that means we can evolve the system and the receivers can evolve with it. So here's an example where the green blocks on the bottom of this chart are the bootstrap. And in between each bootstrap, we have some data. We have more signaling. In this case, we have 3 physical layer pipes, the orange one, the pink one, and the blue one. And for example, it's time division multiplex in order to allow these 3 different things going on. They could all be different services. So perhaps one is some television service, one is some kind of data download, and one might be even a radio service, who knows. And you can also do frequency division multiplexing or layer division, but I'm not going to get into those too much details right now. But one of the most important things about the bootstrap is the evolution of the system. In this diagram, we see that the bootstrap has an important point in it, which is the pointer to the next similar physical layer frame. So in this case, we interleave the next generation frames with the ATSC 3.0 frames, and you share your bandwidth between the two systems. And the receiver receivers pick up the frames that they understand, and they skip the ones that they don't. And that's very important as we want to evolve from, for example, today we use HEVC video encoding. Tomorrow we might use VVC video encoding. And maybe it's not even going to be television services in the future. Maybe it's going to be something that we have not even imagined yet. And in this way, we can start emitting those new services without leaving behind the legacy receivers and all of the people who are using the service on the legacy receiver. So just the quick benefits of the physical layer, many system options, hierarchical control signaling, high robustness, flexible configuration, and synchronization of the basic system parameters to allow the future technology advancements. Many, many flexible functions. Optimization for the broadcaster depending on what their use case is. So moving up the layer, I only want to spend one slide on the transport layer. As you can see in this diagram, we have on the left side broadcast and on the right side broadband. And at the very, very basic level, we have our physical layers, we have our data link layers. But here you see we converge at the Internet Protocol layer. And as we move up the stack, we see that even Dash is shared across the HTTP broadband interface and the broadcast interface. So it's currently the only digital terrestrial standard that specifies IP transport. And it enables many of the convergence scenarios, some of which are quite important in India, where you can converge with other IP networks, such as the cellular network, the Wi-Fi network, and the internet wired network. Okay, so what's better about video? So in this case, for ATSC 3.0, we have specified up to ultra high definition. 8K is possible in the future, but at this time, there does not appear to be enough of a marketplace demand for 8K, but we expect that will come in the future. And when it does, we will be able to evolve the standard to include 8K. We have spatial scalability, high frame rate, high dynamic range using PQ and HLG. So that's like HDR10 plus, HDR10, Dolby Vision, SLHDR1, those kind of systems. And then we also have wide color gamut, which looks fantastic. On the audio side, we definitely have improved spatial resolution. In other words, it sounds more immersive. Really fantastic surround sound, definitely a step in the direction toward more visceral experience with the audio. And then in terms of accessibility, we have the ability to reach those that are hearing impaired and visually impaired with new systems, both video descriptive services, better closed captions in more languages. We can deliver emergency messaging in ways that both visually and hearing impaired people can understand it. And we can do closed signing and dialogue intelligibility. So all these things available for to make sure the message gets to everybody. And for interactivity, as I mentioned before, this is one of the other differences between ATSC 3.0 and DVBT2, which is that the interactive system is based on web technologies. So you guys all familiar with HTML5, cascading style sheets, CSS, and JavaScript. So many people who already know how to design applications and web pages will be able to design applications for the ATSC 3.0 interactive system. Very simple, very straight down the pike, just borrowing from all of the other web standards. The advanced emergency information is a very important piece. And I mentioned before that ATSC has an MOU with IIT Kanpur. This is actually a three-way MOU with ATSC, IITK, and with the AWARN Alliance, which is focused on advanced emergency information, which is extremely key for the broadcast standard and for making sure people and lives are safe. There are four main parts of emergency information. We have the wake up field, which allows any sleeping device that's in standby mode to wake up and check and see what the emergency is. And that's carried in the bootstrap. As I mentioned, that's the most robust part of the signal. And so your receiver can get it even if it's very difficult to receive signals at that point. We have the Advanced Emergency Alert table. This is a signaling table, and I think all of you guys are electrical engineers, so we can get into some little bit of technical detail on this. It basically tells the receiver everything it needs to know about the alert. And we have the interactive piece, which I just mentioned, which allows the broadcaster's application to render the emergency information to the viewer. And lastly, we have some watermarks, which enables critical information to go through even 1.0 or DVBT or any other ecosystem you want. So then we have some security, which is also extremely important. At least in the US, the major broadcast networks are very concerned about security of their content, especially when it's in an internet protocol form. And so we have a studio to transmitter link secure path. We have signed signaling tables so that receivers can validate the source of the emission, make sure, try to protect against man in the middle kind of attacks. And then we have content encryption, which protects the high quality content, high value content, but it also enables some new business models, subscription services, freemium services, pay-per-view. And similar to the interactive system, it's all based on web technologies, common encryption, also called CENC, which is very common in the ecosystem. And this is the one little block that I mentioned in one of the earlier slides, datacasting. So like I said, this is not just about television anymore. ATSC 3.0 is a large digital data delivery pipe. So in India, where you have high power, high tower broadcast system, you could be delivering more than just television services. In fact, it could be done on a low power, low tower system if you wished. It enables the terrestrial broadcast network to compete with other data delivery networks on price and service level for a one-to-many use case. Remember, it's a broadcast downlink only thing. So it works very well with large amounts of data that are intended for many, many devices. Firmware updates, map updates, media services, Internet of Things, smart agriculture, connected cars are just a few of the things that people have in mind for this system. So ATSC 3.0 is a suite of standards. There's many documents. They're all interchangeable, and each one talks about its own specific part, such as video, audio, captions, physical layer, etc. These are all available on the ATSC website for free, atsc.com, atsc.org. So a little bit about terrestrial broadcasting in a mobile world. I think in India, there's what, 1.2 billion cell phones and many, many people watching video services, including linear video services, everybody watching the same thing at the same time. So the Third Generation Partnership Project is another standards development organization, and they develop the standards used for mobile phones, 2G, 3G, 4G, 5G, and TSDSI is one of the original 3GPP 7 partners. The standards are largely designed for two-way communication using a cell phone. We call this unicast. And the digital terrestrial standards like ATSC 3.0 and DVB are designed largely for one-way communication, one-to-many, also known as broadcast. So the broadcast mode is the most efficient way to deliver large amounts of data to many devices at the same time. So everybody's watching the cricket match at the same time, perfect for broadcast. Unicast is the best way to deliver small amounts of data to fewer devices at different times. So each connection is unique, it's got its own data feed. And so even if people are consuming the content at the same time, it's better on broadcast. Whereas if everybody's getting their own unique feed, it's a telephone conversation, it's a Twitter, you know, accessing the internet, watching video on demand. These are good for a unicast. So some examples, live sports, news, software, firmware, map updates, these are all good candidates for broadcast, whereas video on demands, calls, and texts are all good for unicast. So 3GPP, the cellular system, you know, Reliance Jio and all these guys are providing the cellular system. It has a broadcast mode as well as the unicast mode, which most people are familiar. The broadcast mode in 3GPP is called MBMS, or sometimes EMBMS, and sometimes FEMBMS, depending on which generation you're talking about. And the ATSC 3.0 and DVB systems are probably a little bit better than the EMBMS system. mainly because they were designed from the beginning for broadcast, whereas the EMBMS system has to coexist with the unicast system. And so there is some overhead involved. So here again is the Shannon limit slide, similar to the one I provided earlier. And you can see that the ATSC 3.0 system has more efficiency than the MBMS system. ATSC 3.0 is also very good for moving things. So the Doppler shift. How do these systems perform when it comes to the Doppler shift? And you can see that the ATSC 3.0 is very, very robust and capable of handling the Doppler shift. In other words, for faster moving vehicles. We have had trials where the train is going 124 miles per hour. I don't know how many kilometers per hour that is. I'm woefully bad at metrics. But it was going quite fast, and we have no problem getting reception. And so you think about convergence between ATSC 3.0 and LTE 5G, because if you imagine that you have some use cases that are perfect for broadcast and other use cases that are perfect for LTE 5G unicast, then it makes some sense that we can use the different systems for the different use cases for the best efficiency of our spectrum. So there are a number of similarities between ATSC 3.0 and 5G, which will help with these kinds of broadcast and unicast heterogeneous networks. So here's one scenario, and I'm going to highlight this scenario because it's something that has been studied in India. So TSDSI is exploring this concept of broadcast traffic offload. So India has many, many, many cell phones, and people are watching linear television content on their phones. And cell phone ownership and data usage is always rising. So it's a big challenge for the cell phone operators to make sure that there's enough bandwidth for everybody, even if they're watching video content at the same time, maybe even in 4K. Very, very uses a lot of bandwidth. So TSDSI is thinking about a smart network core that monitors the number of devices receiving the same data at the same time on an LTE 5G network. And when the number of devices exceeds a certain threshold, you can move the data from the 5G network onto the digital terrestrial network. No simulcast, and bandwidth savings is the goal. So experimenting with the 3GPP broadcast mode as well, the EMBMS, while also exploring ATSC 3.0 in order to solve this network congestion problem. So the cellular operators in India may prefer to use a DTT spectrum in order to preserve their own spectrum for all the unicast services. So ATSC has formed these teams, as I mentioned, in order to help explore these use cases, in particular within India. Both the India implementation team, specifically for broadcast traffic offload concept, and also planning team on core network technologies, which is probably going to be needed for supporting this use case. So coming back to the career opportunities for students in broadcast, it's not about television so much anymore in this world. We need people who are good RF engineers, radio frequency engineers, web developers who understand HTML5, CSS, and JavaScript. We need IP network engineers who understand how to put together networks, both large and small. There's going to be a lot of data. We need big data analysis. We need experts on cybersecurity and IP network security. But we also need storytellers and journalists. We need people who understand and are interested in standards development. Cloud infrastructure, everything is going to the cloud, including video encoding, as well as the core network systems. And virtual networks, the storytelling, the color science, the compression algorithms, and it goes on and on. So there are a lot of opportunities for young people coming up who are interested in working in the next gen broadcast world. So in summary, ATSC is one of 4 digital terrestrial television standards development organizations in the world. ATSC 3.0 is the newest 2nd generation digital terrestrial television standard. It's not just for television, it's designed for TV and datacasting, non-TV uses. It's designed with fixed and mobile receivers in mind. and it's designed for convergence with other data delivery networks, such as the internet, Wi-Fi, LTE, 5G. Currently, ATSC 3.0 is the most efficient physical layer for one-to-many data delivery in the world, bar none. There is no other system that is more efficient for one-to-many. And India has unique use cases for digital terrestrial television broadcasting, and ATSC teams are working to help support those. And lastly, there are many opportunities as ATSC 3.0 is launched, developed, expanded, and evolved, whether you're working with ATSC 3.0 or DVBT2 or 3GPP EMBMS, there are many, many opportunities in this space. And I think also within IEEE is also working on network convergence with 3GPP. So there's a lot going on in this area. So I tried to go reasonably quickly in order to leave some time for some Q&A. So I'm happy to answer any questions or to return to any of the slides if you want some more detail about any part of what I've presented today. So again, I thank the team at St. Joseph and all the folks that Mira so kindly introduced at the beginning of the webinar, and all of you who've been listening. And I'm happy to take questions if you have any.
Hello, Mom.
Yes,
We have a few questions from the participants.
very good.
Okay, so the first question goes like, what are some of the methods used to determine spectral efficiency of a live digital broadcast network?
So there is quite a lot of test equipment available which can measure how powerful the signal is, how strong it is, and how much data you are pushing through the system. So for example, companies like DECTEC have that capability. I think that in India, a company called Sankhya Labs has developed a number of tools. In Korea, companies like DigiCap have developed tools. So it's an electrical engineering tool which can capture the data which is being delivered, determine how strong the signal is, and how much data is being pushed through the spectrum. In the US, the broadcast television system is divided into 6 megahertz bands. And I believe in India, it uses 8 megahertz bands. So you have 8 megahertz to play with in terms of your bandwidth. And you can have a very, very strong signal which doesn't carry as much data, or you can have a less robust signal which carries a lot of data. And the reason for this trade-off is because in order to have a very strong signal, you devote a lot of your data to error correction. And so what you do is you assign some of your capacity to error correction, which means that it can't carry, user data. But yes, there's tools available in order to measure that capability and the spectral efficiency that you're getting, depending on your configuration.
Okay, thank you, Mom. The next question is, which technique for 3D imaging and visualization, the holography or planoptic imaging, will be dominant in the future 3D television?
Yeah, good question. ATSC has a planning team on future technologies for broadcast, and they are studying these kind of questions. So I think that one of the most important things for these types of use cases is going to be compression. When we go from standard definition to high definition, we need almost 4 times as much data to send this. And then we go from high definition to ultra high definition, times by 4 again. And so the cost of sending this type of very, very rich spatial resolution is very high. So as I mentioned earlier, you have the Japanese Standards Development Organization, and they're very interested in 8K. The reason why they have not finished their 2nd generation broadcasting standard yet is because they need a more advanced video codec in order to send 8K. They need VVC, which is being developed in MPEG right now. But I think about sort of a holographic or a 3D kind of thing. Now you need point cloud encoding. You might need something very, very robust. And so again, thinking about careers and opportunities in standards development organizations, MPEG is working on the video compression standards. And I think that video compression will have to become much, much better in order to be able to deliver those kinds of services with any kind of large scale to, full marketplace.
Okay, thank you, ma'am. The next question, what will be the spectrum band allocated ATSC 3.0?
Yeah, so in the US, ATSC, the television spectrum band runs from low VHF, high VHF, and UHF. In the US, the highest band is 600 megahertz, which is of course very small compared to some of the millimeter wavelengths they talk about for 5G, where you're getting into 20, 30, and 50 gigahertz in terms of the frequency. So in India also, the television bands are, I think they go as high as 700 megahertz band. And above that, I think is allocated probably to the cellular services. But so you have this band, which is going from low VHF, high VHF, UHF, up until 600 or 700 megahertz, depending on where you are in the world. And those frequency bands are carved up into 6, 7, or 8 megahertz bands, depending on where you are in the world. In the US, divided into 6 megahertz bands, and in India, I think into 8 megahertz bands. I think Europe also uses 8 megahertz bands. I think Japan does as well. And so within your bandwidth, your 6, 7, or 8 megahertz, and actually the cellular bands are carved up into 5, 10, 15, 20, like that, bandwidths. So within those bands, you can deliver what you want. If you have if you happen to be in one of the higher bands, you need smaller antennas for the receive equipment. And if you're in the lower bands, like low VHF, you need a very big antenna for your receive equipment. So thinking about how you might want to allocate your use cases, if you're in the low VHF or high VHF, in other words, low frequencies, you might be targeting things like cars, where you can have a very large receive antenna, maybe embedded into the fender of the car or in the roof of a car. Whereas if you're trying to reach a cell phone, which is a very small device, you might be looking at the higher bandwidths for that type of service. So for example, in the US recently, the 600 megahertz band was auctioned off, sold from the TV station owners to the cellular network owners. T-Mobile bought most of the 600 megahertz band, and they had to spend some time developing an antenna for the phone that would operate very well at that frequency, because 600 megahertz is the lowest frequency of bandwidth that they operate in. So they have solved that question, and the expectation is that antennas going as low as 470 megahertz and up could be developed for devices as small as cell phones. When you get below 470 megahertz into lower frequencies, you probably need antennas that are too big for a phone that size, or you'd have to have some kind of external antenna, or you'd need a bigger receive device. Maybe it's a farm equipment, maybe it's a digital signage outside in a city, maybe it's a car. So that's kind of how people are thinking about the spectrum these days.
Okay. Thank you, ma'am. We have one last question. Will there be any overlap between ATSC and cellular communication spectrum bands? So
that's a complicated question. I would say yes and no. So most countries, India included, I believe, the government controls the spectrum, and the government licenses the spectrum to all the various users, whether it be military, whether it be cellular phones, whether it be C-band radio, microphones for white space, and television, radio, FM, AM, all these things. So the government is controlling who gets to occupy which spectrum band of the overall spectrum that's available. And in the US, that's the FCC, Federal Communications Commission. And the FCC has determined that the television is operating in these certain bands, the low VHF, the high VHF, and the UHF up to roughly 600 megahertz. Above that, the US has allocated bands to cellular services, military services, and the list goes on. The map showing what spectrum bands are allocated to what areas of the market is very, very complicated. There's many, many, many users. And the governments watch after all of that. And I think the same is true in India. Under the ministries, they control and determine who gets to use which portions of the spectrum. In your case, Doordarshan is running both Prasar Bharati as well as the radio system. And the ministry is advising Prasar Bharati which part of the spectrum they are allocated and how they can use it. And the same is true in the US. And so unless things change at the government level, the television broadcasters will continue using the bands that they have. In the US, the FCC not only determines which areas of the spectrum you can use, but they also determine how you may use them. In other words, which system can you use? And in the US, both ATSC 1.0 and ATSC 3.0 are permitted to be used in the spectrum bands by the FCC, by the government. In India, I believe that DVBT and DVBT2 are also both allowed in the DTT spectrum. So how do you use these and what is the convergence about? So unless the government makes some kind of change, I think we can assume that the TV operators will operate in the TV bands and the cellular operators will operate in their cellular bands. But in the case of the broadcast traffic offload, we can envision that the cellular operators will move some of their traffic from their networks, from their spectrum bands, onto a DTT spectrum band. And that would allow the cellular bands to be more available for unicast services, such as phone calls and video on demand and text messages and all the things that we like to use in our daily lives. So thinking about how you could do some kind of convergence, as I mentioned, 3GPP has a method of doing broadcast services one-to-many called EMBMS or FEMBMS, depending on which generation you're thinking about. And what can happen is a cellular operator like a Vodafone or whoever can allocate some of their spectrum to these broadcast capabilities. So they can have, let's say they have 100 megahertz of spectrum band that they play with. And they can say, okay, well, I'm going to devote 10, 20, 30 megahertz of my spectrum to broadcast FEMBMS. And I'm going to devote the other balance of it to unicast services, normal 3GPP, LTE, 5G, or 3G, or whatever. What that means, though, is that they have devoted 10, 20, 30% of their own spectrum to broadcast services. And what they would like to do potentially is to take all of those broadcast services and move them completely off their spectrum, so that all of the broadcast services could be carried by a television operator down in the lower frequencies. So, you know, it's the question, which I think is being contemplated in IITK and other areas of India, is how can we move this data from the cellular spectrum to the television spectrum in order to open up the cellular spectrum for more unicast services and in order to fully utilize the television broadcasting spectrum. Kind of similar in many countries, the number of people who watch television using the over-the-air system on a TV, for example, with an antenna on the rooftop, in many countries is small. In India, I think it's very, very small. In the US, it's on the order of 20%, maybe a little less. In Europe, it varies a lot. So some countries less than 2%, and they're going to not even use the television airwaves for this anymore. And in other countries, it's as much as 70%, such as in Italy like 70% of people watch this over-the-air broadcasting using a television set with an antenna. In those countries where lots and lots and lots of people are watching over-the-air television, you can imagine that the television spectrum is very well used. It's got a very powerful use case and a lot of people rely on it. In countries where very few people watch over-the-air television, you could argue that even if the television is the best content in the world and everybody loves it, if nobody's using those spectrum bands in that way, then maybe the spectrum is underutilized and we could find a better way to use the spectrum. So that's what some countries are exploring. How can we take this broadcast spectrum all the way low VHF, high VHF, and UHF? How can we take this and make the most use of it we possibly can? Because spectrum is kind of a limited commodity and a very precious resource for every country. And they want to use their spectrum as efficiently and well as they can. So if you only have 2% of people watching TV using this method, then we have to think to ourselves, is there a better use for this spectrum? Or how can we maximize the use of this spectrum, not just for certain content, but for our overall economy and for the strength of our country? And so that's what ATSC 3.0 is trying to do, is if you have a television operator who is operating services on these spectrum bands, how can we make sure that these spectrum bands are working as hard for our economy and moving the country forward as well as possible, because it's a scarce resource, this spectrum. And that's what 3.0 is hoping to do, is to open up these kind of opportunities so that the data that you're pushing through in these spectrum bands is extremely valuable and highly utilized, and moving the economy forward as much as possible.
Thank you, ma'am. Thank you for your patience. Now I invite Dr. G. Rohini, ma'am, Professor and Head of Lab Affairs, to express her gratitude.
Thank you, Dharani. Good morning, Ms. Madeline, ma'am. Very good morning to all. Yeah. Myself, Dr. Rohini, Professor. I deem it a great privilege to have been asked to extend the vote of thanks on this webinar session on behalf of Department of Electronics and Communication Engineering, St. Joseph Institute of Technology, St. Joseph Group of Institutions. Every human brain is both a broadcasting and receiving station for the vibration of thought. First, I would like to thank our guest speaker, Ms. MADELINE MNOLAND, President at Advanced Television System Committee, Boston, USA, for her informative speech on ATSC 3.0. Thank you, ma'am, for finding time and giving information on ATSC and Digital Terrestrial Broadcast Standards, development and technical advancements in ATSC 3.0, heterogeneous network ecosystems and use cases, in spite of your busy schedule for the SAVANT 2.0 webinar series. My heartfelt thanks to our beloved Chairman Sir, Dr. B. Babu Manoharan, for his consistent upkeep in conduction of this webinar. My sincere thanks to our Managing Director, Ma'am, Mrs. B. Jesipriya, and our Director, Sir, Mr. B. Sashisekhar, for their guidance in conduction of this webinar. I would like to express my gratitude to our Principal, Sir, Dr. P. Ravichandran, for his support to conduct this webinar. I also thank our Head of the Department and IEEE Chapter Advisor, Dr. C. Gnana Kausalya, and all other faculties of our department for organizing this event successfully. A special mention of thanks to our Students Chair, IEEE WIE Chair, Ms. Dharani, and Student Vice Chair, Ms. Vinyana Soundarya, 3rd year ECE, and all other IEEE students for aiding in conduction of this webinar. I am also very grateful to all the students, faculties, research scholars from India and other countries for their active participation in this webinar. Thank you all. Thank you, participants. Thank you, ma'am, once again.
Thank you very much.
Yeah.
Thank you, ma'am. Thank you so much for taking out time from your busy schedule and joining us today.
Dharani, you want to say something like?
Yes, ma'am. So I would like to thank our department heads and each one of our IEEE staff coordinators, student coordinators for taking an initiative and bringing this platform together for the fellow students. And I thank all the participants for their active participation. And our next webinar is by an eminent speaker, Ms. Elena Messina, who will be giving a talk on from automatic to autonomous, defining industrial vehicle capabilities, which is scheduled tomorrow at 4:30 p.m. So the interested participants can register in the same link and attend the session tomorrow. So thank you all.
Thank you, ma'am.
Thank you very much.